next speaker, Adrita Chakraborty, who will talk about butterflies visited for asymptotically Lifshitz black holes.
Thank you very much. Thank you for having me here. It's a great opportunity to present my talk in this esteemed conference. So this work has been done in collaboration with my colleagues Ms. Bonostri and Ms. Nivedita from IIT Guwahati and IIT Kharagpur respectively in India. So this is based on this archive A-print. So I have organized my talk in this way. Firstly, I will briefly describe about some basic aspects of asymptotical Lifshitz black hole. Then I will give some brief explanation of what butterfly velocity is and what Lyapunov exponent is in the context of chaos or chaotic system. And here our main focus is to study the chaotic features, namely butterfly velocity and Lyapunov exponent, by using these three quantum mechanical methods, namely entanglement wedge, pose skipping, and the derivation of out of time order correlators in the context of asymptotically Lifshitz black holes. And here we want to show that these three methods are equally competent and equivalent to produce these chaotic features in the Lifshitz black hole. So also we have derived the iconal phase shifts and Lyapunov exponent at the classical level, and then I will conclude my work with some future scope. So asymptotically Lifshitz black holes are some black hole geometries which asymptotically meet the non-relativistic Lifshitz spacetime that follows this kind of Lifshitz scaling, where there appears an anisotropy along the time direction because of this dynamical critical exponent which parameterizes the anisotropy. So that is why it breaks the conformality of the usual ADS black hole, and also it breaks the Lorentz symmetry. And the Lifshitz black hole geometry in t plus 1 dimension can be written in this form with this blackening factor here, where ZH defines the horizon. And this kind of black holes are found to be thermodynamically stable, and its temperature can be derived in terms of the anisotropy index as these. And here I want to mention that the legitimate holographic dual theory for such black hole is the d-dimensional non-relativistic Lifshitz field theory at finite temperature. So in analogy with the thermal CFT, here also we can do some compactification in the flat spacetime while constructing this thermal Lifshitz field theory along the time direction. But as you can see, the time direction has the dimension which is the xith power of the length dimension. So the inverse temperature is here is the beta to the power xi, which we will be using in our work afterwards by denoting it only in terms of beta. So our beta will be this new beta which is beta to the power xi here. So chaos in any disordered system defines the growing local perturbations when we deviate the initial conditions infinitesimally. So in that case there appears considerable changes in the later sets of such systems due to the small deviation in the initial conditions, and if we take two initial points which are arbitrarily close together, then due to this effect which is known as the butterfly effect, gets separated from each other over time at an exponential rate and giving us this kind of structure while plotting the trajectories, and that is why it is known as the butterfly effect. It is a significant consequence of having chaos in any physical system. So to study chaos in any physical system, we can study these two salient features which are butterfly velocity and Lyapunov exponent. Butterfly velocity gives us the constant rate of propagation of chaos in any local system, while the Lyapunov exponent gives us the rate of separation between the initial points because of chaos. So when the Lyapunov exponent is positive in any physical system, then it implies that the system is chaotic. And in any quantum system, the butterfly effect represents the effect of such small deviation in its Hamiltonian system and its constant rate of propagation with the butterfly velocity. So for any two derivative gravity, it has been found that the Lyapunov exponent follows an upper bound which goes like 2 pi by beta. Beta is the inverse temperature. So previously in Lifshitz field theory or such theories with Lifshitz scaling. Chaos has been studied by different kind of explorations, like people have probed circular strings in the holographic Lifshitz spacetime and found them to be chaotic string solutions. Also in quantum Lifshitz model, which is a 3D Lifshitz field theory with xi equals 2, shows some chaotic growth in its marginally irrelevant operators. Also holographically, people have explored the scrambling properties in some generic asymptotic black holes, which also include Lifshitz black holes. So in our study, we will focus on the study of equivalence between these three methods to study the chaotic properties of asymptotic Lifshitz black hole. So let us start with the entanglement wedge method. Entanglement wedge is basically a slice of the bulk. Most conveniently, it is taken as a constant time slice, which lies upon the boundary, and it captures all the quantum information of the boundary. So when there is a local perturbation imposed upon a boundary state, it causes scrambling in the bulk information after a late time evolution, and this scrambling can be thought in the bulk prescription as the change of the shape of the trajectory of any infalling particle inside the extremal Ryu-Takanagi surface, and the rate of change of this kind of trajectory is constant, which is given as the butterfly velocity. So the extremal RT surface in any holographic system may be determined by using the Ryu-Takanagi prescription, which deals with this holographic entanglement entropy computation, where this gamma gives is the induced metric for the chosen system. So to find out the determinant of this gamma, we have to parameterize the extremal RT surface in a suitable way. Here for our work, in Lifshitz black hole, we have parameterized the radial coordinate z in this way, and then we wrote the induced metric by Taylor expanding in terms of around epsilon equals 0, and took the terms up to first order. Then by solving the Euler-Lagrange equation of this Lagrangian here, that is by using the variational principle and setting the variation of this induced metric to be 0, we got yr as a Bessel function of first kind with these expressions of n and mu. And then we saw that when there is a chaotic growth, then RT surface starts to reach towards the boundary, and its tip touches the boundary, and at that position this yr tends to give us some exponential factor here. Then from this we derive the butterfly velocity as a function of the dimension, space dimension of the metric and the anisotropy index in the near horizon limit. So here we saw that when this anisotropy index is going to 1, then the butterfly velocity is the same as that of the ADS black hole, which should be the case because for xi tends to 1, we must get conformal symmetry restored in our present scenario. So let us see what happens when we start with the pose skipping method. So pose skipping method is a very competent way to study chaos in different physical systems. These pose skipping points appear in the retarded 2-point energy density functions when the lines of poles and zeros get intersected. Then at these intersection points a would-be pole gets skipped, and holographically these pole skipping points can be understood as the perturbation in the bulk metric. So at the pole skipping points, chaos can be measured by studying the characterizing frequency omega star and momentum k star, which are related to lambda L and Vb in this way. So here we studied for 3D Lifshitz black hole, and we went to the convenient coordinate system for such method, which is Eddington-Finkelstein coordinate system. Then we perturbed the metric in this way and took the perturbed Einstein equation in the near horizon limit for its vanishing case, which appears only for this mode, which is the TRV mode of the stress tensor. This happens because the retarded Green's function is governed by only these two modes during the chaotic growth. Because of these two conditions, this is the gauge condition and this is the tracelessness condition. And then by solving the perturbed Einstein equation in near horizon limit, that is the delta TRV equals 0, we got these expressions for the pole skipping points, the frequencies and momentum for the pole skipping points, where RH becomes a function of temperature and the anisotropy index. So, all of them are the non-trivial functions of the anisotropy index because of the presence of anisotropy in this non-relativistic black hole geometry. And then by using these two relations, we obtained from these expressions Lyapunov exponent as 2 pi t and butterfly velocity as this. Now, if we go back to this situation, then if d equals 2, then we can see that butterfly velocity is exactly similar to what we have obtained in the pole skipping method. So, here we can see that these two methods are giving us exactly similar results for the chaotic features, and hence they can be used as equivalent methods to study chaos in Lifshitz black hole. So, let us go to the out of time ordered correlations. So, it is also a very significant method to derive out of time ordered correlators to study chaos. These are some correlators, so which can represent some 2 particle high energy gravitational scattering between particles moving along the 2 horizons of a double sided Kruskal version of a black hole. So, this is a 4-point function where we can see two operators V and W, which represent these two particles moving along the horizons. And here you can see that there is a part which appears to be out of time ordered, and when this part decreases, then there is an increase in the this 4-point function, and this 4-point function gives us the measure of chaos. So, when it increases because of the decrease in OTOC, then we get significant butterfly effect in our system. So, this 4-point function can be studied holographically as this exponential factor, where T star is the scrambling time. And to get our out of time ordered correlators in the present scenario, we rigorously constructed the Kruskal version of double sided Kruskal version of 2 plus 1D Lifshitz black hole, which I did not show here because of its complicated calculations and all, and then perturbed this metric by using a gravitational shock wave along one of the horizons. Then we took this back reacted Einstein's equation, where it involves both the back reactions of the matter part and the shock wave part. And then by solving this Einstein's equation, we got this expression for this 4-point function in the holographic bulk prescription. So, here by comparing this one with this general form in the near horizon limit, we got similar results for the Lyapunov exponent and the butterfly velocity in the 2 plus 1D Lifshitz black hole. Here I want to mention that here the scrambling time and this m in the near horizon limit are derived by using the metric components of the Kruskal form of 3D Lifshitz black hole. So, all the 3 cases are giving us the exactly similar results for butterfly velocity as well as for Lyapunov exponent. So, we can say that in the context of asymptotically Lifshitz black hole, all these methods can be used equivalently and as some equally competent ways to study chaos. So, let me give some descriptions of what we have calculated for iconal phase and Lyapunov exponent by using classical approach. So, iconal phase is just this similar kind of phase factor that probes the amplitude of gravitational high energy scattering. So, here we dealt with the heavy light scattering in the classical approach by considering this expression of iconal phase from the bulk prescription. This gives us the bulk phase shift. Here Pt is the conserved energy, Px is the conserved momentum, and delta t and delta x are the deflections along the time and x directions respectively. So, for the complicacy of our integrations, we just did calculations in the near boundary and near horizon zones for near boundary zone and for some condition in the near horizon zone, which is this. We are getting imaginary iconal phase shifts, thereby this gives us some notions of inelastic scattering in these two cases, while for this case in near horizon zone we are getting real iconal phase shift, which gives us elastic scattering scenario. So, here we can see that because of the anisotropic structure of our bulk, we are getting different kinds of scattering scenarios in near boundary and near horizon zones. So, here Z0 is the turning point of the null geodesic forward geometry, and gamma is the impact parameter, which is the ratio of Px to Pt. And also we have derived the Lyapunov exponent by using the classical approach, and this is the first principle for exploring the Lyapunov exponent, where P effective is the effective potential along the radial direction. For any circular motion, we have used these two conditions, that is at the turning point both P effective and its first derivative go to 0, and using these conditions we got this Lyapunov exponent for our case, and we saw that it is real and this gives us the notion of having any unstable trajectory. That means by calculating these two quantities in classical approach, we also obtain the chaotic structure of the Lifshitz black hole. So, also we commented upon some limitations on the choice of turning point. This appears because of the presence of arbitrary anisotropy here, because this is our null geodesic equation, and here the anisotropy index is arbitrary. It can assume any integer or any fractional value. So, depending upon its value, this polynomial is either integer ordered or fractional ordered. So, it's to calculate the exact values of Z0 is not that much easy to do analytically. So, we just commented that only the valid roots for our case are the real roots which lie within the singularity and the boundary, and we saw that following these conditions we can see this Z0 cannot assume the values 1, which is the horizon, and the Z0 equals 0 is also not possible, which is the boundary for any arbitrary gamma. So, turning point should not be at the horizon or at the boundary, and also we found that the Lyapunov exponent is inconsistent at the horizon and at the boundary. So, these two values of Z0 should be excluded for our study, and if someone wishes to calculate the exact values of Z0 for such approach, then one may go for some suitable polynomial distribution to find its solution, but we did not include it in our study. It can be an open area. So, just a summary that in our study we explored the butterfly effects by using these three different methods, which are entanglement wedge method, pole skipping method, and the derivation of out of time ordered correlators. And we saw that all of these methods are giving us the exact equal results for VB and lambda L, and hence we can assert that these three methods are equivalent for studying chaos in the context of asymptotically Lifshitz black hole. And also we studied the classical chaos by deriving iconal phase and Lyapunov exponents starting from a classical approach, and we saw that all the quantities that we have derived both classically and quantum mechanically are the non-trivial functions of the anisotropy index of our present geometry. And also we found some different kinds of scattering scenarios in the vicinity of boundary and the horizon because of the presence of arbitrary anisotropy in our geometry. And also we can comment that as the iconal phase shifts are all the non-trivial functions of psi, so we can expect anisotropy dependent scattering cross sections in the in different cases, like in the near boundary zone or in near horizon zone. And also we postulated some potential limitations on the choices of turning points of the null geodesic. And as some future aspects, we can study the any possible connection between what we obtained in classical approach and what we obtained in quantum approach, because here you can see that this phase factor is giving us some kind of hypergeometric function from the classical approach, whereas it is giving us some kind of exponential structure in the quantum mechanical approach. So it would be interesting to find some kind of connections between the phase factors derived from quantum and classical contexts. And also we can go for a systematic construction of the dual thermophile double sets to find out the explicit out of time ordered correlators for the thermal Lifshitz field theories. So thank you.
Thank you very much. We have one question.
So this classical Lacunal exponent, does this have an interpretation holographically, and how do you define it exactly? How do you define, so this classical Lacunal exponent you were talking about, so how do you define this, and does it have a holographic interpretation?
It's here this gives us the phase shift, this particular expression gives us the phase shift in the bulk. I mean if you consider an infalling particle inside the bulk, then in case of that particle, if you consider the scattering, then it gives us the phase shift.
And how is the phase shift related to the Lacunal exponent?
This I'm not quite sure about it. I think I myself searched it, but for this study we could not find anything. So I'm afraid that I cannot tell on the basis of this thing, but we can study it in further maybe. It's just two different measurements that we did from the classical context.
Thank you.
Great. I think in the interest of time we have to thank you again.